March 30th, Physics 151. I looked at the presentations, and they're about where they should be right now. Starting to get an idea of what's going on with the rides, what's involved with some of them, and we'll flesh things out as we go. But one thing many of the rides involve, as does, for instance, the motion of the Earth around the Sun, which we want to incorporate into saving the Earth, is something moving in a circle. So today we will look at aspects of things moving into a circle, and then apply that and the appropriate motions for other rides to the rides and the forces, and saving the Earth, of course. So if something's going to be moving in a circle, okay, let's stop that program. Something's going to be moving in a circle. It's the forces we've seen don't seem to be a constant force or a uniform force, because the force is not always pointed the same direction. So let's look at things moving in a circle. It's not a straight line or a parabola, which is what we've seen for a constant force. So let's run this. There's a circle, and we want something to follow the path of that circle. Right now we're not applying any forces, so it's just going in a straight line. That white arrow indicates the direction and size of a little change of momentum, a little momentary force that we can apply to the circle, to the moving object. So for instance, if I do this, every time I click the mouse I apply the force, and it keeps going faster and faster. Now I'm applying a force going the other way, and it's going to come back this way. So this is not making it move in a circle. I could make it stop altogether. Every time I click the mouse, it gives a little change momentum, a momentary force in the direction of the arrow and with the size of the arrow. Now you could try doing this with the simulation. Think of it as kind of a game. The link is up on the Moodle. Or if you've got space and a ball, you could go out and try to give a ball a little kicks so that it goes in a circle. A circle at constant speed is what we're going to be going for. Okay, let's bump this back a little. So give that a try. See if you can apply little bumps to the ball to make it move in a circle. Okay, so let's run this again. And let's see if I can push it along the arc of the circle once it gets running. I'll try to push it along the arc of the circle here. And it's not doing so well. Okay, so just trying to do a force along the circle didn't seem to work very well. Let's try this again. You play around a little bit, you might find that you get a little better luck if you simply make the force point towards the center of the circle. Okay, now you have to click it just the right way, so I'm not quite on the circle, but at least I'm following a closed path. Sort of circular-like. So to make something move in a circle, it appears that you need to do something that is not just trying to push it around the circle, but push it towards the middle of the circle. Okay, this can stop now. So in particular, we're going to try to make something move in a circle call the radius of the circle r. And we want it moving at a velocity. Remember, the velocity is tangent to the path. And in particular, we're going to look at the case where the speed is a constant. So another question is, what can we then say about the acceleration? Is it 0 or not 0? Think about that for a second, what your reaction is. So one reaction is that, well, if the speed is a constant, then that means that the time derivative of the speed is 0, which would seem to imply that acceleration is a constant, is 0, because acceleration, after all, is the derivative of the speed. Except that's not quite true. Acceleration is the derivative of velocity. Velocity is a vector. It includes the speed and a direction indicated by this unit vector. So to have an acceleration, you have to have that the derivative of the speed and the direction together would have to be 0. But we've got the product rule. This would be dv dt times v hat plus v times the derivative of the unit vector with time. Okay, this kind of derivative is normal, and in this case the derivative is 0 because the speed is in fact a constant. But this is a derivative of a vector. That's something a little different. It's the change of the direction that the velocity vector is pointing. So if I draw the circle again, at this point on the path, the velocity vector is tangent to the circle. At this point of the path, it is again tangent to the circle. We can see if this is changing by subtracting them. Remember, to subtract, you have to put the vector's tail to tail. So if we redraw this one, v2 over here, then we can subtract them by drawing the arrow that goes from the first one to the second one. That is the change of velocity vector, which is proportional to the acceleration. So the gist of it is that this factor, the rate of change of the direction of the velocity vector, is not 0. So to have acceleration 0, we would have to have both the speed constant and maintaining the same direction. And going in a circle, you are not maintaining the direction. So therefore, the acceleration for going in a circle cannot be 0. You're changing direction. So you can have a constant speed but still be accelerating if you're changing the direction of motion. Okay, so there's a little confusing terminology here. When we do have a constant velocity vector, that is sometimes referred to as uniform motion. So, for instance, Newton's first law says that something will maintain uniform motion if there are no interactions, which is a way of saying that the forces acting on it add up to 0. And that's an if and only if. It goes both ways. If the forces add on 0, the velocity stays constant. And that is referred to as uniform motion, a constant, a uniform velocity. This type of motion, where something is going in a circle at constant speed, Commonly, people refer to that as uniform circular motion, and that's confusing. The uniform part is coming about because the speed is constant, but it is not uniform motion because the velocity is not constant. So with the phrase uniform circular motion, the uniform refers to the speed, not the velocity. In the phrase uniform motion, the uniform refers to the velocity. The speed is also constant, but also the direction. Uniform circular motion, the speed is constant, but the direction is not constant. Okay. What does this mean, for instance? This means that something going in uniform circular motion is not a Newton's first law situation, but you do have to apply Newton's second law. You have to use the idea that the summation of all the forces acting is the mass times whatever the acceleration is. And this piece of it, the acceleration, is what we're going to talk about for a little bit. How do we figure out that acceleration? It means, for instance, that in the space station, where we speak of them as being weightless, but we do know that the gravity force is acting on them. The force is not zero. Well, the acceleration is not zero. They are, in fact, responding freely to the force that is acting on them. And we're going to see that force will make them move in a circle. So they are not weightless. The gravity force is not zero. They are accelerating, but everything around them, as we shall see, is accelerating in the same way. As opposed to near the Earth's surface, where you throw something up and it falls back down because it is accelerating differently from the surface of the Earth. In this case, where something is moving in a circle, constant speed, there is a total force. You take all of the real forces and add them up. That equals the mass times acceleration. But in this situation, the summation of the forces is given the name centripetal force. And the acceleration, F vector c, centripetal force, is then the mass times what we call the centripetal acceleration. In this case, these are simply saying that these are the force and acceleration in a case where something is moving in a circle. We're going to go through many examples of this. Centripetal force is not an actual force. It is the sum of forces. So when we're looking at the forces in the rides or acting on a space station, we will not add in a centripetal force. That is simply a name for the total force that makes it move in a circle. And the name for the acceleration it has is centripetal acceleration. Okay, so let us now get an idea of how we can figure out the acceleration something has when it moves in a circle, given the properties of the motion and the properties of the circle. And we will be able to apply that to situations like a satellite orbiting the Earth orbiting the Sun, or some of the rides we're looking at, many of which things are moving in a circle. So therefore the total force must be centripetal, something that acts to push it in a circle. Okay, so your book goes through a somewhat complex derivation for how you can calculate the acceleration of something moving in a circle at constant speed. I will show you something that's visual and make an analogy that gives the same result. If you want the rigorous math, you can look in the book. So let's look at something moving in a circle. So this little red ball is moving in a circle. These blue arrows are the position vectors. I'm taking the origin to be the center of the circle. And I'm drawing two successive position vectors. So this was a previous and the later one. And the green arrows are showing you the differences between position vectors. So the green arrows are telling you about the velocity vectors. And you can see they are tangent to the circles. So in every case, the green arrow points from a previous position to a next position. Now over here, I'm redrawing the green arrows and showing two successive velocities. I'm just drawing them tail to tail so I can subtract them. Previously we did that by moving them along the circle. Here I'm just drawing them in a circle of their own. The red arrows therefore are indicating acceleration because they're a new velocity minus an old velocity, so it's proportional to acceleration. And when I copy the red arrow back onto this circle, you can see it's pointing back in the opposite direction of the blue arrow towards the center of the circle. Now, what you see is that the blue arrows are rotating at a certain rate, and the green arrows are related to that. And over here, the green arrows are rotating at a certain rate, and the red arrows are related to that. And in both cases, these sets of arrows are rotating at the same rate, the rate at which we're going around the circle. So, here's where we make an analogy. Let's move this camera over a little. Okay. So on the left, we have the velocity arrows, which have some relation to the position arrows because they are parts of the arc of a circle. And on the right, we have acceleration arrows, which have a relation to the velocity arrows. The size of the velocity arrow is the radius of the circle on the right. The size of the position arrow is the radius of the circle on the left. The ratio of these follows the value of pi and also follows the rate at which things are going around in the circle. So therefore, these two ratios are the same. The behavior of the green arrows with respect to the blue arrows on the left is the same as the behavior of the red arrows with respect to the green arrows on the right. So from that, we can say that this acceleration, which again we're calling a centripetal acceleration, is given by the speed squared divided by the radius of the circle. Okay, this is kind of a picture proof. The more detailed proof of mathematics is in the book, but this will give you the gist of it, and I will not expect you to reproduce the math that's in the book. Okay, so many of the rides involve circles. The actual orbit of the Earth involves a circle, so when we save the Earth, we will certainly be thinking of circles. Let's get a little practice with the acceleration of something moving in a circle. So I will do an application, and then we'll have you work through one. There's a concept called a geosynchronous orbit. That is the idea that if we have the Earth, we can have a satellite orbiting the Earth at some height above the surface of the Earth. The dashed line is the orbit of a satellite. And it is constantly moving in that circle. In a sense, it is constantly falling towards the center of the Earth As it moves to the side, it is constantly falling towards the center of the Earth. So that circle represents, in a sense, an infinite fall, falling forever. Let's tone this brightness down a little. So we can make a satellite orbit the Earth in such a way that the number t, which we'll call the period of the orbit, which is the time for one orbit, and a geosynchronous period would be in the case that it orbits the Earth in 24 hours, the time it takes the Earth to rotate. In that case, the satellite is orbiting the Earth at the same rate that points on the Earth are rotating, and therefore the satellite is staying above a particular point of the Earth. It doesn't fall to the Earth. Well, actually, it is falling to the Earth, but it is moving and the Earth is rotating at the same rate. So from our point of view, it appears to be staying up in the sky. This would seem to be an example where Newton's first law doesn't seem to be working, because we're looking at that satellite up in the sky. We know gravity is acting on it, but it's not falling down from our point of view. Well, the way to look at it is, well, in a sense, Newton's first law does not apply to our point of view because we are not in what's called a Newtonian point of view. So from our point of view, the satellite appears to be staying in the sky and not falling, even though gravity is acting on it. That does not mean there is some mysterious force holding it up in the sky. It means that we are in a point of view where we ourselves are rotating. And if you are in a rotating point of view, then your point of view, Newton's laws will not work. And in that point of view, to try to apply Newton's laws, you would have to invent some sort of mysterious force that's holding the satellite up. In this class, we will always take the Newtonian point of view. So if you see a situation where it looks like Newton's first law is not working, where something is maintaining constant motion, even though there's a total force acting on it that's not zero, then you have to consider, well, maybe I'm not in a Newtonian point of view. Another example would be a car going around a curve, and if you're in the seat of the car and aren't wearing a seatbelt, say you're over here on the right, there's nobody on the left, there's nobody on the right, the car is going this way. As the car goes around the curve, from your point of view in the car, you seem to be thrown to the right. Whereas what's actually happening is the car is moving around to the left, and you are tending to go in a straight line. So in the Newtonian point of view, for you to go in the circle, there would have to be some force pushing you in the circle. If there's not, you're just going to fly off on a tangent. In the car's point of view, there seems to be a mysterious force pulling you along. So the point of view of someone outside the car would be a Newtonian point of view. You go in the straight line. The point of view of inside of the car is not Newtonian. And Newton's first law isn't working. We will take the Newtonian point of view. Okay, so back to the satellite. We want a geosynchronous satellite. The time for one orbit is 24 hours. And we want to know the height above the Earth's surface. So redrawing the orbit of the satellite. It's moving with a velocity v, or some speed v that we want to be constant. And what is that speed? Well, we don't know anything about that speed, but we can think about the radius of the orbit, and 2 pi r times that, which is the circumference of the orbit, divided by the period. That would be the speed. It goes one circumference in one period, so that will be the speed. That radius, in turn, if I look at the radius of the Earth and the radius of the orbit and the height of the satellite, then we have that the radius of the orbit of the satellite is the radius of the Earth plus the height of the orbit above the surface of the Earth. Okay, what else do we know? We can look this up. This is what we're trying to find. So we don't know h, we don't know v, but we do know something else. We know that to be going in a circle, it has to have a certain centripetal acceleration given by v squared over the radius of the orbit. So squaring v, that will be 4 pi squared r squared over t squared divided by the radius of the orbit, so the centripetal acceleration has to equal 4 pi squared r over t squared. And it has the right dimensions, a distance per time per time. Well, we still don't have enough information because the height h that we don't know is still hidden in here, and we don't have the acceleration. But we do have Newton's law of gravity. In this case, the only force acting is the gravity force. So that must be the centripetal force. The total force is the net force. In this case, the only force is gravity, so the net force is a gravity force. And for something moving in a circle, the net force has to equal the force that's making it go in a circle, which is the mass times the centripetal acceleration. So the gravity force, the total force, has to be 4 pi squared r over t squared times the mass of the satellite. And let's put ms here for mass of satellite. And we know from Newton's law of gravity that the gravity force has a value of big G times the mass of the Earth times the mass of the satellite divided by the distance between their centers squared. So that has to equal 4 pi squared r over t squared times the mass of the satellite. Okay, so the quantity we're trying to find is in r. So let's find big R first, and then we can subtract the radius of the Earth and get h. Okay, so I'm working with this equation. The mass of the satellite is going to cancel out. I can cross multiply by r squared and also by t squared. So I'll do some algebra. Big G times the mass of the Earth divided by 4 pi squared t squared equals r cubed. And now we have everything we need. We know big G, we can look up the mass of the Earth, and we have said what we want the period to be. This equation that says that the radius of the orbit cubed is proportional to the period squared is actually a manifestation of one of Kepler's laws. Kepler looked at a whole bunch of planetary motion data taken by Tycho Brahe, and he found that all of that data for each planet obeyed 3 laws. And one of the laws was that the cube of the radius of the orbit was proportional to the square of the period of the orbit, and the proportionality constant was the same for all of the planets. In this case, the mass would be the mass of the sun. Then Newton came along and said that, yes, that is the result you would get from my law of gravity. Well, I don't know if he put it quite that way. But because Newton's law of gravity does lead to Kepler's law, that gives us a reason to obey Newton's law of gravity. Okay, so the last piece is we need to take the cubed root of everything. So the cubed root of big G times the mass of the Earth divided by 4 pi squared times the period squared. That will be the radius of the orbit that we need. Okay, so we've written down the number for big G before. 6.67 times 10 to the minus 11 newtons times meters squared per kilogram squared. Mass of the Earth, we can look that up. 5.97 times 10 to the 24. And the period of the orbit is 1 day. I will just go ahead and convert 1 day into seconds here. So 24 hours times 3600 seconds per hour is 8.64 times 10 to the 4. And all of that is going to be divided by 4 pi squared. And then all of that is under the cubed root symbol. Okay, we should check the units before writing down the answer, because this is a fairly complicated calculation. So a Newton is equivalent to a kilogram times meter per second squared. And then we have that times a meter squared divided by a kilogram squared. That's this. Then it's multiplied by a kilogram and multiplied by a second squared. This is squared under here. You would have caught that mistake, so 2 points. And that's it, because 4 pi squared is unitless. So we have kilograms, 2 of them on top and on the bottom. We have a meter cubed on top, second square on top, on bottom cancels. So we have a meter cubed and the cubed root of that, so this does work out to be meters. Okay. And I'll let you ballpark the number. The answer is that the radius of the orbit is 4.22 times 10 to the 7 meters. And if you subtract the radius of the Earth, that gives you that the height of the orbit is going to be 3.6 times 10 to the 7 meters. Okay, so here's one for you to try out. I said that when you use Newton's laws, you can reproduce the Kepler's law. So I will have you kind of do that in reverse, using that the law of gravity is big G times, say, the mass of the sun times, say, the mass of the Earth, divided by the distance from the sun to the Earth squared. Using the information, the mass of the sun is 1.999 times 10 to the 30th. The mass of the Earth, as we just saw, is 5.97 times 10 to the 24th kilograms. And the distance from the center of the sun to the center of the Earth for the Earth's orbit, 1.48 times 10 to the 11. And big G, 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. Also using the idea that in this case the gravity force acting on the Earth is the only force, so therefore it must equal the mass of the Earth times the centripetal acceleration of the Earth, velocity squared, divided by the distance from the Sun to the Earth. And the idea that the velocity of the Earth around its orbit will be 2 pi times the radius of its orbit divided by the period of the Earth's orbit. Call that TE, which you know to be 1 year. Actually, pretend you don't know big G. That's the number you expect to get. And if all of this works, that's the number you will get. But pretend you don't know big G, but combine everything and solve for big G and show that this number for big G, which was found by doing experiments on the Earth, actually also works for the orbit of the Earth. So you can try working through that math, and I will put up the solution. I will look at the comments that you have made on the different presentations. I didn't want to give my comments first because I wanted you to look at them first. And then we will start considering the sorts of forces that are in the rides, applying them to the rides, and to some extent follow a path that the groups will determine. So one thing the groups can think about, and I will probably have you turn in something to this extent, and that is, what is, in a sense, the goal of the project for your ride? So the goal, for instance, might be to determine how much tension there is in whatever is supporting the ride, or how fast the ride is going given what you can see happening in the ride, or what the friction coefficient has to be for the ride to work. So in every case, you could analyze it with a variety of different goals. So think about what you would like a goal to be. You want to analyze and find out what friction would make it work, what's the fastest it could rotate at and work properly, given reasonable constraints on how people can accelerate, how long can it be if it's rotating at a certain rate. In every case, try to identify something that if we can measure or estimate the other quantities, we can use physics to determine something interesting. So given that, I will see you on Wednesday, and I will make some commentary of my own on yours after I've looked at your commentary, and we'll see where we go. See you later.